Okay, so we've looked at rotations. Now let's look at 3D angular velocity. Okay, it's always good to relate this to 2D, right? So in 2D, we looked specifically at rotations about the z-axis, right? So we have x, y, and then the z points out, and then we did rotations. And corresponding to that rotation is a rotation angular velocity of theta dot, where of course this is angle theta turned. And so theta dot k is the rotation about the z-axis, where k is the unit vector along the z-axis. So in 2D, we wrote down omega z. Okay, I'm using vector notation here. Omega z is a vector now. And we really didn't care about vectors there because, since everything was in 2D, so we didn't really have to put vectors or keep track of axes. But here in 3D, we'll have to. So this is something in 2D. Now, if you go in, so this is for the speed. Angular speed, rather. So let's just call this a fact 1 in 2D, and that's for the angular speed. Okay, the second fact is how do you find the linear speed? The linear speed in 2D is, and I don't think I wrote down the formula quite this way, but the speed can be written as omega cross r, okay, where omega is the angular speed. So in this case, omega is going to be omega z, and r is whatever the vector is. So the velocity of point P, so there is an object in 2D, and we want to find the velocity of point P. Then the velocity of point P is going to be omega z, which is theta dot k times the vector r. So here r will be this. So r will be typically in the two-dimensional plane. So there'll be an x component and the y component. The cross there is the cross product. Okay, and this is the formula for linear speed. So those are the things going on in 2-dimension. Okay, now if you go to 3-dimension, in 3 dimensions, following is what happens. So we've looked at, so here, by the way, theta dot is, you can think of that as some kind of you can think of theta as an angle, but it's also kind of an Euler parameter in 2D. And then if you take the derivative of that Euler parameter, get theta dot, then you get, or what they call Euler rate, then you get angular speed along the z-axis. So can we extend this to 3D? Can we write omega now is a 3-dimensional vector? So like omega x, omega z, right? So we've looked at phi about x, theta about y, and psi about z. So the question is, can we write it like this? So I is, by the way, unit vector along the y-axis. Theta dot is a unit vector about the y-axis. So theta dot times j plus psi dot times k. Okay, so it turns out you cannot write this way. These are the Euler rates. Okay, the Euler is the corresponding the time derivative of the Euler parameters we defined. Okay, so omega. So fact 1 does not hold true in 3D. And fact 1 was that does not hold true. So the rate of change of Euler parameters is not the angular speed of the object. That is kind of the critical thing. So remember that. Other thing which we wrote down, V equals omega cross R, is actually true no matter you are in 2D or 3D. So fact 2 holds true in 3D. So you can always use V equals omega cross R to to find the linear speed in 3 dimensions. Okay. So now the question is, how do we, so if omega is not equal to the rate of change of Euler parameters, then the question is how to get omega in 3D. Okay, so that's what we're going to go for, getting the angular speed in 3 dimensions. So before I show you how to get that, I need to introduce what is known as skew symmetric matrices. So let's talk about skew symmetric matrices because they will be useful in finding angular rotation in 3 dimensions. So skew symmetric matrices. Okay, and we'll denote the skew symmetric matrix with S. The way we write S is if there was a parameter A with A1, A2, A3, then the skew symmetric matrix would be something like this: A3, A2, 0, minus A1. So this is the diagonal element is all 0. The off diagonal element looks like this, and then the elements below the diagonal will be exactly the same as above the diagonal, but with but will be negative of whatever is above the diagonal. So it'll be A3 and then minus A2 and plus A1. Okay. So now from this, so A here, you can think of A as a vector of A1, A2, A3. And some people like to use AX, AY, AZ. That's fine. Okay. So there are some properties of a skew symmetric matrix which will be helpful. Number one is if you take S of A and then you take S transpose of A, so take S, take this transpose, sum it up with S of A, you will see that it's simply equal to 0. Okay, and you can just visually verify this, that it is equal to 0. The second property is that if you do A cross B, okay, where A is a vector, right? A is A1I plus B1, sorry, my bad. A1I plus A2J plus A3K, and B is B1I plus B2J plus B3K. That's A, and this is B. So you want to find A cross B, and there's a way to do it using hand calculation, A cross B. You could actually write this as S of A times B. Okay, so remember that this is a vector, this is a matrix, and this is a vector. This is 3, 3, this is 3, 1, and this one is you're basically multiplying a vector. So you will see that it basically will give you something which is, the product here is going to be 3, 1, right? Because if you take vector product of 2 vectors, you'll get the same vector. And here, when you do 3 times 3 times 3 by 1, you'll get 3, 1. So you'll get the same thing, but sometimes it's much easier to do the matrix multiplication times the vector. So MATLAB, for example, is very good at doing matrix multiplication. So here's an advantage. You can take A, you can write a skew symmetric matrix corresponding to A, and then take the product with B. And actually, I'll show you that this actually works out. Okay, it's actually easy to prove this. And then the third property, which I'm not going to prove, is that R times S of A times R transpose, where R is a rotation matrix, can also be written as S times R of A times B. This only if R is a rotation matrix. Okay, so this is a proof which I think is slightly more complicated, but the proof is in one of the books I recommended was Pong's book on robot modeling and control. His book has the proof, but you could check this for a specific value of R and A and B that this works out. Why did I write B here? This shouldn't be B. It's S of R of A. Okay, so there are 3 properties. We can actually prove 2. Let's just 2 is true. And I think it was neat. I didn't believe that was true when I saw it, but it actually is pretty true. So so this might be a review of vector multiplication or cross product, sorry. If you want to do A cross B, then you do it this way. I, J, K. Then you write A1, A2, A3, B1, B2, B3. And then you just take the determinant. So you take the first row, first column, and then you multiply whatever is here together in this way, A2 times B3 minus A3 times B2. Then you take minus J because next one should be minus. And then you take A1 times B3 minus B1 times A3. And then finally, K, we would have A1 times B2 minus A2 times B1. And so in other words, what we've effectively got is, if you want to write in terms of a vector, right? It's a vector because it's ijk. You could write it as A2B3 minus A3B2. That's the first component. The second component, I'm just going to make this minus go inside, which means that I need to swap this out. So B1, A3 will be first with a positive sign, minus A1, B3, and then A1, B2 minus A2, B1. So that's A cross B. Okay, now let's do this using this formula, S of A times B. So S of A, as we saw, was 0 minus A3, A2 minus A1. So A3 minus A2, A1. And then B is simply B1, B2, B3. So let's take this cross product. Sorry, it's this matrix times vector product. So 0 times B1 is 0. So then we have minus A3 times B2 plus A2 times B3. Then for the second one, we have A3 times B1 minus A1 times B3. And then finally, minus A2 times B1 and plus A1 times B2. And so what we need to do now is check if these agree. So we have this A2, B3, which is right second term minus A3, B2, that checks. And then the second one is B1, A3, B1, A3 minus A1, B3. So that checks. And then finally we have A1, B2, A1, B2, and A2, B1, A2, B1. So that checks too. So you can see that A cross B is in fact S of A times B. Which we checked. Okay, so that is a small proof. Now let's go to the next part. Okay, on actually getting a formula for angular speed. This is just some of the preliminaries we would need. Okay. So first of all, I wrote down C0 equals RZ RY Rx times C3. Okay, what I'm going to do is I'm going to write this in a slightly different way. So this is my rotation matrix R. This, as I said, is going to be my position in body frame. So I'll call that RB. And then this is a vector in global frame. So I'll not put anything, just make it 0. So RB is body frame. And R is in world frame. And R is RZ psi, RY theta, Rx phi. And the other thing to remember is that when the body frame, the position vector does not change. It remains the same. It's simply going to be the position in body frame is time invariant, because if you remember the figure I showed you, when the frame changes, when the body rotates, the body frame coordinates X, Y, Z will still point along the same directions in which they were originally pointing. So if you remember the Z, we just go back to there. And that's kind of a key point. So let's just go there. I'll just quickly show it to you. So right here, yeah, so Z, for example, was always along the largest square area, and then same here, you can see, and then same over here and there. So everywhere the Z for example, points along the largest face of the cuboid. And that's the key thing. So RB is fixed in that sense. Okay, so once we have that, now let's try to get to the angular speed. So what I'm going to do is differentiate with respect to time or t. So we have r dot, so that's the time derivative, equals r dot rb plus r times rb dot. Okay, now as I said, the vector in body frame does not change with time, it's the same thing. So this vector, so this rb dot should be equal to 0. So we have r dot times rb. Okay, so we just keep that in mind. Okay, now let's take the property of a rotation matrix. The property is r times r transpose is I. Okay, and then differentiate this with respect to time. So we have r dot times r transpose plus r times r dot transpose equals derivative of I is 0. Okay, now I'm going to do something like this. I'm going to keep the first term as it is. And the second term, I'm going to do the following. I'm going to take the transpose and transpose. Okay, when I take 2 transpose, we know that 2 transpose is the same as the original vector, so it doesn't change the matrix, it remains the same. What I'm going to do next is I'm going to use this transpose to do something. So we know there's a property which is if you want to find AB transpose, that is the same as B transpose A transpose. That's the property of matrices. I'm going to use that property. So here, this is my A, this is my B. So I would write that as B transpose times A transpose. So R dot transpose is my B. So transpose of that. And then R is my A, transpose of that, following this formula. And then the transpose here just remains there, right? So this transpose just stays. It's this same one, doesn't change. Okay, so I got that. Now let's me try to manipulate that. So that equals 0. Okay, so R dot transpose of transpose is the same as R dot. And then R transpose is R transpose. Okay, so now we have an interesting thing, which is this is the same as this vector. Sorry, this matrix R dot R transpose is the same as that matrix R dot R transpose. And that is equal to 0. This implies that R dot R transpose must be a skew symmetric matrix. So this must be some skew symmetric matrix. And I'm just going to put A for now. Okay, so where A is that element which shows up in the matrix. So this should be S. Okay, and that is a skew symmetric matrix. So I can say that S of A plus S transpose of A equals 0. Okay, I still don't know what A is, but I just showed you that when you take the derivative in this fashion, you get a skew symmetric matrix. So I can say now that S of A needs to be found is equals R dot times R transpose. This is something which you have to remember, okay, where R is the rotation matrix. Okay, now let's do the following. Well, we can rewrite this as S of A equals R dot R transpose. Let's post multiply by R. Okay, so we have S of R times R equals R dot R transpose times R. But we know that R transpose times R is simply I. And so what we can do is we can now write this as R dot equals S of A times R. So this is just telling you how to find the rate of change of R. You can just take S of A times R. Instead of actually using diff, you can actually use this property. Okay, now let's come to the final part before we stop for today. That is actually finding the angular speed using some of the formulas we've already derived. Okay, so I'm going to take this down. Okay, I'm going to use this R dot equals small r dot equals capital R dot times RB. So we have small r dot is capital R dot times RB. And also remember that R equals capital R times RB. This is from what we got this formula for R, small r dot. Okay, now we have written down a formula for R dot, right? And that is here. R dot is S of A times R. I'm just going to copy it down. So R dot is S of A times R. Is that right? Yeah, it's right. Okay. That's from 2. Okay, so I just keep that in mind. Now what I'm going to do is I'm going to sub this in here. So we have S of A times RB, sorry, S of A times R times RB. Okay, now what you notice here is that R times RB is simply small r. So I write it down. From, sorry, I should write it here. From 3. Okay, so R dot is S of A times R. But we know that A cross B is the same as A, so S of A times B. So this is something which we proved. And so I'm going to write this as is S of A. So I write it as A crossed with B. B is here R, right? So this is equal to B. So using this formula. So now we've written down R dot equals A cross R. But we know that V equals omega R. Okay, what is V? V is basically rate of change of position, which is R dot equals omega cross R. And so if you compare this expression now, let's call this 4, this 5. So from 4 and 5, we can see that A has to be equal to omega. So the angular speed is the thing which is inside the skew symmetric matrix. So now we can do the following. We can rewrite some of the equations I wrote down. So I wrote down R dot R transpose is S of A, that's simply S of omega. And then I wrote down R dot equals S of A, so that'll be S of omega times R. So those are my formulas for angular speed. Okay, so the angular speed doesn't quite come out here as a formula like omega equals something, but it is something you can get if you know the rotation matrix. If you know R, you take R dot, you take R transpose, you multiply them, and what will come out of that will be the skew symmetric matrix, which in turn will give you the rotations. What is S of omega? It'll be something like this: omega minus omega z, omega y, omega x, 0, omega z minus omega y, omega x, and 0. That's what S of omega will look like. And what we'll do next class, so basically here we found how omega is rated. So this shows how omega is related to R, okay, or the rotation matrix. What's R? R is basically consists of RZ, RY, RX, or what's RZ psi, RY theta, RX phi. But then the question is, how is omega related to the Euler angle Euler rates of Euler parameters. So that would be psi dot, theta dot, phi dot. So that's something which we'll do next time. I will show you how they are related. So R dot equals S of omega times R. And so since we're interested in S of omega, we can write S of omega is R dot times, we have to pre-multiply, post-multiply with R in R transpose. And so we get R, so let me just do that here. It's easier this way. R dot R transpose is S of omega R times R transpose, but R times R transpose is identity. And so we can write S of omega equals R dot times R transpose, where remember that R is RZ, and that's, I think we used psi for rotation about Z axis. We used theta for rotation about Y axis, and we used phi for rotation about the X axis. Okay, so given this, we need to find what omega is and somehow related it to these Euler parameters. So what we're going to do now is, and you see that's kind of tedious calculation, but it's doable. We're going to actually find R dot and put it in there and then simplify. So let's start doing that. So we have R dot, which is d dt of R, which is R z, R y, R x times R transpose. And so we can write S of omega equals, now if we're doing d dt of three terms, we need to do the individual derivative and treat the other two as constant like we do in chain rule. So here's what we'll do. We do R c dot, R y, R x, R transpose plus R z kept is a constant, so keep it as it is. Take the derivative of the second term. And then finally, RZ, RY, RX dot R transpose. Okay, now I need to basically simplify these things. In fact, I need to put RZ, the formula for RZ is here, right? And then take the derivative with respect to time and simplify. That's what I'm going to do. So let's call this 1. Let's call this 2. And let's call this 3. And so I'm going to simplify this individually. So let's start with 1. Okay, so the first one is RZ dot, RY, RX, R transpose. And so what I'm going to do is I'm going to expand out R, which is given right here. So it's RZ times RY times RX. So RZ times RY times Rx transpose. Now the property of the transpose is that when you take the transpose of two matrices A and B, so AB transpose, the whole transpose is B transpose times A transpose. So if you want to extend that to 3D, three rotational matrices or three matrices in general, then you need to reverse them and then take the transpose of individual ones. That will be Rx transpose, RY transpose, RZ transpose. I sort of flip them and then I take the transpose. Now we can see that this thing is simply I, and then once that becomes I, this and this, the RY and RY transpose will be equal to I, and we'll be left with simply RZ dot RZ transpose. Okay. Okay, now what is RZ? RZ dot, well, we know that R equals S of, what's that? S of omega, or dot equals S of omega times R transpose. But if you want to find what RZ dot is, then it'll be S of omega Z, RZ transpose. The same formula holds true. But what is S of omega Z? Omega Z is simply, remember it's phi, theta, and psi. So psi dot k. That's the rotation about the Z axis. So now we need to put that right over there. So RZ times RZ trans, something is not right. This is not right. Sorry. So this is not R transpose, just R. Okay, so now if you take the transpose of both sides, that is, you multiply post multiply with RZ transpose, you get S of psi dot k. Okay, which means that now I can sub that here. So this will be simply S of psi dot k. So we've simplified the first expression to give S of psi dot k. Okay, now let's go to the second one, which is RZ RY dot RX R transpose. I'm going to simplify that one next. Okay, the second one is RZ RY dot RX R transpose. Again, let's write down the expression for R. Sorry, it should be Z Y X, and then I can use the property of transpose to get Rx, Ry, Rz. But this thing here is simply I, and so we're left with Rz, Ry dot, Ry, Rz transpose. Now we can do the same trick, which is R dot is S of omega times R. But if you want to find R dot of Y, it's S of omega Y R. But what is S of omega Y? It's basically the rotation about the Y axis. So that's J times the rotation in this case is going to be theta dot times R. This should be Y. So then we can write R dot Y R transpose, that is post multiplying it with RY transpose, gives us S theta dot J. Okay, so this goes in right here, and we get RZ S of theta dot J RZ transpose. Now there's another property which I wrote down earlier, and that property is that if you have rotational matrix R, then R of S of A times R transpose is simply S of RA. Okay, and so you got to use it here. So you can see it's exactly of the same form. So we write this as S of RZ times theta dot J, right? Because RZ is R here, and then we just have to put that in. So S goes with RZ theta dot goes inside. And so this is the simplification for the second term. And then finally, the third term, I'll write down first, which was RZ RY RX dot times R transpose. So I'm going to expand that R similarly. RZ RY RX transpose RZ RY RX dot. And now I flip all these things, RX RY RZ transpose. Okay, so again, what I can do is I can write R dot equals S of omega times R. So Rx dot will be S of omega X Rx. But S of omega X is a rotation about the I-axis by an angle of phi. So phi dot I times Rx. Post multiply with Rx transpose gives me Rx transpose equals S of phi dot I, and I can sub that in right here to get RZ RY S of phi dot I equals, times RY RZ. I'm going to do a trick, which is the inverse of what I did earlier, which is I basically took AB the whole transpose as P transpose A transpose. So what I can do here is I can write this as RZ RY times the whole transpose. So if you take the transpose of that, you'd end up with I think RY transpose times RZ transpose. That's right. Okay, so this, you can think of this as a matrix R, and then I'm going to use the property of skew symmetric matrix, which says that R S of A, R transpose is R of, sorry, S of R of A. Right? So here we have S of R of A. R is this term. So RZ, RY, A, which is phi dot I. Okay, so that's my simplification for the third term. So very close to getting what we are. So we are just going to now pull everything together. So I'm going to write expression for S of omega now, but I have all these three terms simplified. So I'm just going to do that. So this is what you get if you put all these terms together. So we have S of omega equals, the first term was S of psi dot k. The second term was S of RC theta dot J. And the third term was RZ RY phi dot I. Now, if you have a sum of three skew symmetric matrices, then it's easy to verify that the sum of individual is equal to S of the whole thing, which means that you can write as P dot K plus RC theta dot J plus RC RY phi dot I. So this is the property of a skew symmetric matrix. And now we can actually compare the two sides. We have omega equals phi dot K plus RC theta dot J plus RC RY phi dot I. So that is my angular speed of the body in actually it's in the fixed frame or inertial frame. Okay, so angular velocity in fixed frame. Now you can write this like in the following way. Omega equals psi dot, the K is 001 plus RZ, theta dot is so J is 010 plus RZ RY phi I is 100. So if you take this and simplify all the things down, you'll end up with something like this. 10, sorry, it should be cosine psi cosine theta minus sine psi 0 cosine theta sine psi cosine psi 0 minus sine theta 0 1 phi dot theta dot dot. Okay, so that's the formula for omega in terms of Euler rates. Angular velocity in fixed frame. Okay, so if you wrote this as if you wrote this as A, and then this thing as, let's call it the capital theta dot equals omega, right? And then if you try to, so given the Euler rates, you can find angular speed. If you were to do the opposite, which is you were to find the angular rates, Euler rates given the angular speeds in fixed frame, you have to do A inverse times omega. Now it turns out in the A, when you do the A inverse, you will see that the determinant, so this needs the determinant of A, right? In fact, it is, I believe it's cofactors of divided by determinant of A. Now, the determinant of A actually is cosine of theta. Okay, so what happens when cosine theta equals 0? Determinant A is 0. When determinant A is 0, the inverse is not defined, and then bad things will happen, which means that it will say that for the given angular speed, it will tell you that Euler rates are infinity. Okay, and if the Euler rates are infinite, it doesn't make sense. How can an object have infinite speeds? So that is not a problem with the object. The speeds are not infinite. In fact, the speeds are finite, but there's a problem with the representation. The representation does not allow us to represent angular speeds when certain configuration treat. And that configuration is you can have anything for phi and psi, but if theta is cos theta is 0 or theta equal pi by 2, then this will just fail. So when theta equals pi by 2, then A inverse is not defined, and we have what is known as, this is called as Gimbal Lock. Okay, and it's a problem with using Euler angles. Okay, the solution is to use quaternion. Okay, and if you use quaternions, you don't have to worry. Now, most times people don't really, I mean, people use quaternions all the time, but some cases you don't have to worry about this problem, because in some scenarios, if your rigid body undergoes some rotation and theta is never equal to pi by 2, then you don't have to really worry about anything. So in case of humanoids and biped robots, we never really have this crazy tumbling motion where we hit theta equals pi by 2. So by far, we don't have to really worry about the gimbal lock. There are some cases where if you have some of the joints, if there are 3 joints and you're trying to represent them using Euler rates, then you might have a problem again. But you've got to be careful. But for most, by far, I don't really see a problem using this kind of rotation for humanoids. Okay, so that's about gimbal lock. Now, there's some things here which I want to point out, which is so we found angular speed in fixed frame. That's omega. Okay, we can also find the angular velocity in body frame. Okay, so that's another important thing which I think we should know. And the other important thing which I think we should know is that I have actually unnecessarily complicated this derivation, right? I did the steps where I did this 3 steps. Right, I took this derivatives and there were 3 expressions, and then I need to simplify all of them and get the final value for S of omega omega. It turns out that there's an intuitive way of deriving that formula, and maybe that this is, some people like this way, the mathematical way, but I'll show you a simpler way of deriving the same formula, which I wrote down here. Right, this formula. I'll show how to write this formula in a much simpler way, just by visualizing the configuration. So this might be another way, you can say it's another way of deriving the formula. So let me show you how to do that. Okay, let's just pull in my notes. Okay, so here's a shorter way of deriving the simpler way of deriving omega. Okay, so here how we will do it. So first of all, let's try to understand what's going on here. There are 3 rotations. Okay, so there's X, Y, Z. That's how you start. Then you rotate about psi about the Z axis. Okay. Then when we undergo rotations by, so Z, this is the new X, this is the new Y. Okay. Next, we undergo rotation about the Y axis by theta. So this will be like this. The new Z, so I'll show double because it's the second rotation. Then this is hard, so let me just put it like this. X double prime. So that's going to be, so this is theta, and then I should probably show psi like this. Okay. And then the final rotation is, we show the X double prime, C double prime, and Y remains as it is. And the final rotation is about the X-axis. So about X-axis, counterclockwise. So we'll end up with something like this: Y triple prime, C triple prime, and that rotation is phi. Okay, so we've got all these rotations. Now let's see how to derive this in a much simpler way. Okay, so we are trying to write a formula for omega, and that's the problem. So how do you find angular speed in world frame? Well, you can actually see it this way. We want to find angular speed in this frame. That's the world frame, right? So we see that it consists of three things. One is there is psi dot about Z. Okay, Z is this axis. There is theta dot about Y prime. Okay, here. And then there is phi dot about X double prime, right? That's what it is. Now, these Z, Y, and X are in different frames, but there's a way in which these can be related to each other. So let's do that. So first of all, psi dot Z is simply our K, and K, as I said, is in the fixed frame. Now we have theta dot, and Y is the new Y, but that Y was obtained from this Y prime, which is right here, was obtained from the fixed frame by rotating about the Z axis. So in order to find what Y prime is, that's simply the rotation about the Z axis times the vector in frame Y, which is this vector Y, which means that it is simply J. So this is basically the net Y prime, which I get if I rotate the original by angle of psi. And then we have phi dot, that is X double prime. So X double prime, it came from Rx, so it came from this rotation. So it came from R theta or R Y. But before that, there was another rotation, R Z. So that rotation then takes me to this frame. So Ry times, the Ry was all about, so X double, so if I want to find the unit vector along X axis in this frame, I just need to do Ry times I. So that gives me X double prime, but that gives me that in frame, in the previous frame, which is this. And then if I want to go from this frame to the first frame, then I need to pre-multiply with RZ. And so all I need to do here is say RZ, RY times I. And then what I can do is I can move things around a little bit. Phi dot K plus RZ theta dot J plus RZ, RY phi dot I. But this thing, the first quantity is actually, let's see, it's it's the same formula. Just quickly check. It's Yeah, it's basically the same formula. So if you look at this formula, same formula as derived earlier. Okay, so we can go and check this. So RZ theta dot and RZ RY phi dot. So if you go back and check here, it's the same formula, which is obtained by doing this lengthy calculation. So this is perhaps a simpler way of deriving the formula without actually doing all that math. Where was I? Okay, so we got that. Now, few things. This is about when you're doing these calculations for more complex robots. This is just 3 rotations. If you want to do this successively, there are like n rotations or n transformations. Then you can actually do this calculation. There's a formula which relates this. So we just talked about 3 transformations from 0. See, that's the fixed frame. And from there, we went to frame 1, from there, frame 2, and from the frame 3. And this was rotation about the z-axis, rotation about the y-axis, and rotation about the axis. So that formula was valid for this. But what if you had n rotations, 1, 2, 3, 4, and so on? So if we can write the rotation matrix for this is R10. Cleaner. So what if we have more rotations like this? So we have R10, R21, R32, R43, and so on till Rn n-1. So if you have this thing where you have multiple rotations, then you can actually write a formula for the nth rotation as follows. Omega n0 is omega 10 plus R10 omega 21, where omega 21 now is the rotation angular speed of frame 2 with respect to frame 1. It's the same as what we had here for theta dot. That relates the angular speed of frame 2 with respect to frame 1, or frame 1 with respect to frame 0, plus R20 omega 32 plus so on, or n-10 omega n-1. So this is the formula you want to sort of use rather than using that generic formula, which is very specific through 3 to 1. So if you had 1 to 3 or anything else, you can use this formula. What I have found is it's more useful to use the recursive formula. And we'll use the recursive formula when we'll do the humanoid derivation, because you'll have to find the angular speed of each of the links. So omega 1 with respect to 0, omega 2 with respect to 0, omega 3 with respect to 0. So you can use this recursive formula. Omega 20 is omega 10 plus R10 omega 21. Omega 30 is omega 20 plus R20 omega 3 with respect to 2. Omega 40 equals omega 30 plus R3 with respect to 0, omega 4 with respect to 3. So note that once you found omega 20, you basically use it here. And then this is something which you know, because you know the angular speed in 2 frames. It just keeps going on till you reach omega n0 equals omega 0 n-1 plus R n-10 omega n-1. So I suggest that you use this formula in this fashion. And if you use it this fashion, you'll automatically recover this above formula, omega n0, by using it recursively. So this is useful for derivation. Okay. Talked about angular speed in fixed frame, omega. Sometimes you're interested in the angular speed in the body frame. What I mean by that is, let's say that this is the angular velocity. So by the way, this is a small omega is the capitalized counterpart of omega is this omega, the capital omega. And let's say that represents the angular velocity in body frame. So in this case, I'm interested in what is the angular speed in this frame, the third frame, not in the first one. Okay, so how do I do that? Well, the one way to do it is to actually do it the intuitive way. It's much easier than doing it through the math, which is, remember I showed you how to derive it this way. So we can do a similar derivation for that. So let me just pick this up for my derivation. Copy, and let's paste it here. Okay. So angular velocity in body frame, which is capital omega. Okay, so I can do it in the reverse way now. What I need to do is, first is going to be rotation about the x-axis. So it will be phi dot x double I, that's the first one. So everything here would be in terms of x double dot, y double dot, z double dot. Then I would have theta dot about y prime. So that doesn't change. And then I would have psi dot about z. Okay, so that remains the same as before, except that, so that's the same formula which I wrote for omega. The only thing which will change here is instead of expressing everything in terms of x, y, z frame, I need to express about x double prime, y double prime, z double prime. So the first item remains the same. We don't change it. The second one is y. And now I need to relate y with this one. So when I go from this to this, remember I did rz times the vector in the second frame. I need to do the transpose now. So what I'll do here is I'll write transpose of the transpose is going to be the vector which helps me to go from this frame to that frame. So that is going to be rotation about the x-axis. So in this case, it's going to be rx transpose times y double prime. And then I have to go for z. I need to go 2 times. So I need to do 2 transposes. So it will be rx transpose times ry transpose z double prime. And the reason I go rx transpose times ry transpose is because when you go from here back, when you go from here to backwards, you do post multiplication. If you go from left to right, you do pre-multiplication like I did before. So now what I can do is I can write this as phi dot. We call that vector as I prime. So this is I prime, j prime, and z prime, or k prime. Then this will be phi dot I prime plus theta dot rx transpose j prime plus rx transpose ry transpose k prime. Okay, and so my angular velocity now in the body frame is going to be this thing. Okay, where I prime, j prime, k prime are unit vectors in body frame. Okay, not I, j, k, which are vectors in the fixed frame. Okay, so we'll see where this is useful. You'll see that this is useful when we find the angular, when we take the kinetic energy due to rotations. You will see that it's more beneficial to use the angular speed in body frame because the inertia vectors are expressed in body frame rather than using the angular speed in fixed frame. Okay, so that will come later on, but I just want to remember that this is more useful than the other formula, but you need both of them nevertheless because sometimes you might have to switch between them. Okay, so then we can actually take this for an n-link robot, right? We have 0 to 1 to 2 to 3 and so on till n. And the question is, how do you find the angular speed in body frame for all these things? So omega n equals n minus 1 plus rn n minus 1 transpose omega n minus 1 n minus 2 plus or n minus 1 or n minus 2 transpose omega n minus 2, n minus 3. You just keep going all the way to reach Rn1 transpose omega 1, 0. And this, I think, is kind of complex, more complex than the previous formula. But the best thing you can do is to actually use this recursively. So that way it's much easier to remember, write, and useful for derivations, because you have to find the angular speed in body frame for each of those links as you go on a serial chain. So here's how you do it. Angular velocity in body frame 1 is omega 1, 0. 2 is omega 2, 1 plus R2, 1 transpose 1. Omega 3 equals small omega 3 plus R3, 2 transpose 2. And just keep going to reach phi n equals omega n, n minus 1 plus R n, n minus 1 transpose n minus 1. Okay, so you can use either of them, but I recommend using the second one because it's much easy to develop in the code. So recursive. Okay, and just like I'm going to copy this. So let's take this. Copy. So just like the previous one, we can actually expand this expression out. Okay, so basically write down the formulas for different things. You'll end up with this formula for the angular speed in body frame with respect to the Euler angles. Cos phi minus sin phi minus sin theta cos theta sin phi cos theta phi dot theta dot psi dot. And then if you take the determinant of omega, you will see that it again equals to cosine theta, which should not be equal to 0 when theta, which is equal to 0 when theta equals pi divided by 2 or 90 degrees, and that's where you get a gimbal lock. So no matter what you do in the body frame, you always end up with, or fixed frame, you end up with a gimbal lock when theta is pi by 2. And this is, remember, it's only true for 3, 2, 1 z, y, x, that you get a gimbal lock when the rotation about the y-axis is pi divided by 2. If you use a different notation like 1, 2, 3 or 1, 3, 1, you might get a gimbal lock at a different configuration. So you need to be very mindful about what configuration you get a gimbal lock and accordingly use it. So in this case, we don't have a problem with this notation for humanoid, but for a different notation, you might actually have a problem. You have to be careful of what you use. So, for example, if you get a gimbal lock at theta equals 0 or phi equals 0, then that can sometimes be problematic for humanoids. You want to avoid those notations.